Hello everyone and welcome. My name is Carmen Gugutal and I'm your host today and your presenter for this webinar. I was just waiting a few more minutes because I was looking at the attendees that they were just coming in, so therefore this small delay of a few minutes. Initially, the webinar was supposed to be presented by one of our application specialists, then Dr. Dan Dumitrescu. Unfortunately, due to some personal problems today, he is not available. Therefore, on a very short notice, I'm here with you, and hopefully I can give you a good feeling about the applications of Crystal16 and everything I can share with you about solid form screening and development of a solid form. So with this said, before I I hope you see my slides, yes. Before I just start, I would like to just give you a bit of a few technical details to share with you. The webinar will last about 45 minutes, hopefully including with questions, so about 30 to 45 minutes. This webinar is being recorded and will be made available to all of you in the coming days. Most probably tomorrow or the day after tomorrow, you will receive an email where you can track back the recording on our website, as well as some additional information related to the application notes and articles that we are going to make available for all of you. If you have any type of questions, please do share them with me by making use of the chat function of this webinar. And if after the webinar you think that you still have some questions and you need a bit more information from us, we will be happy to share everything we can and we have with you. Just feel free to either write to my email address. I see many no names. You know my email address, or the email of Technobis Crystallization Systems. Write to us at info@crystallizationsystems.com, and I will do my best in the coming days together with the team here at Technobis to answer all your questions and give our support. And with that said, for those, although I see, as I mentioned to you, a lot of known names that joined us today, a bit about crystallization system, Technobis Crystallization Systems. We are a Dutch company on the market since 2005, located in the Netherlands. We are a world-leading technology provider for solid-state research, process development, and formulation. Anything related to crystallization, process development, and formulation, almost everything we can help you with our system. We have 3 products in our portfolio: the Crystal Breeder, Crystal16, and the crystalline instrument. And as you can see, quite a few customers. We have a worldwide presence with more than 600 instruments already installed in the field. But to give you a bit more of the flavor of the history of the Technobis Crystallization Systems and our instruments, because we are a company technology driven and involved a lot in development, and how through the year how we started back in 2003 with the maybe some of you recognize this metal box back in 2003 when we started with the idea with the Crystal16, the version 1 and, of the Crystal16 brought on the market in 2005. Our other products, Crystalline, Crystal Breeder, and what was newly launched not so long time ago, a few weeks ago, version 3 of our most popular instrument, the Crystal16, as we like to call it, and not only as we like, we call it the new industry standard. Because you would also find it in quite a lot of laboratories around the world. So this is just a bit of a view of how Technobis Crystallization System or Crystallization Systems brought this portfolio on the market through the years, and stay tuned, much more to come. And with this said, sorry, I'm just struggling between many, between different monitors. It has been quite a while since I haven't done a webinar, so please bear with me. So as I mentioned, our instruments, all our portfolio, if you look at the solid form landscape and actually the pipeline on how you develop an active ingredient, here more towards pharma, an active pharmaceutical ingredient, they address quite a big part of the development of such an API, starting from early, very early stage discovery, where the crystal breeder with a small volume addresses any type of form screening, together with the Crystal16, so actually with the initial polymorph screening, salt screening, co-crystal screening. There is your instrument to use later on when you go towards developing and optimizing your crystallization process or your formulation process. The Crystalline can address quite well those needs, still in parallel with the Crystal16, and later on when you actually already brought on the market, or you are ready to bring to the market the API or your active ingredient, when you would like to perform an extensive screening, IP screening, to protect your molecule as much as possible. Again, Crystal16 is your best tool to use for such exercise. And now, enough said about all about the product portfolio. But today, as promoted also with this webinar, I'm going to focus on the Crystal16, on the newly launched instrument a few weeks ago. And its applications. What can you do with a Crystal16? And hopefully by the end of this webinar, I can give you a good impression of and ideas what you can do and how versatile is such a tool and instrument to have in your lab. And maybe you can also share with me at the end of the webinar any ideas how you would you use differently the Crystal16. The unibody crafted instrument designed by us, the scientists, for you, the scientists. As I mentioned, introduced not so long time ago, this new version, but already on the market, addressing the main issues of crystallization problems, let's say, for quite some time. Last year we also celebrated 16 years of Crystal16, and we are proud to see that actually it was mentioned the use of an instrument in more than 200 articles, papers out there, mentioned in a lot of patents, and of course quite a lot of instruments that we have proudly installed all over the world. The Crystal16, for those of you that do not know or didn't hear about the newest version, shortly, 16 reactor instrument that you can heat and cool in a controlled manner using vials, the HPLC vials, the 1 milliliter vials. With 4 independent reactors, and now this Crystal16 can, with air, dry air, just dry air, reach with all 4 block reactors in parallel minus 20 degrees, and can go up to 150 degrees. If there is the need of going to an even lower temperature, minus 25 degrees can also be reached. It can be connected to a chiller, and you can reach minus 25 degrees. Even if you set your temperature lower on the chiller, I have done not so long time ago some tests, you can even reach minus 30 degrees. The steering, the mixing still overhead, and top steering and bottom and netting steering. Overhead with this hook designed to, in a way, not to grind your crystals, so to protect a bit, not to break your crystals while you are performing an experiment. Turbidity, so the transmissivity technology, it still comes with this, and the software is quite different. And with that said, I go a bit more into details, what is really different and what is new with this instrument that we have just brought on the market. One of the main improvements or new features is the transmissivity. So this turbidity, if you want to call it like that, range. And here you have a comparison where we compared the V2 with the version 3, the current version now, and where we tried by using naphtalometric units, standards actually, to see how much we could we see, let's say, at this moment versus what it used to be. And as you can see here, we really enlarged the window what you can detect with this instrument. So we can see much lower concentrations if you go and look at this range here, and also here at the upper part. At higher concentrations, we also see much more than we used to see with the Crystal16 up to now. This is just one piece of data. There is much more out there. It's from a recent test that we have done at the University of Rouen, which I'm very thankful that they have helped us also with this test. And as you can see, clearly see, this was done on a compound in a solvent, different heating cooling rates. And the old the data collected with the old Crystal16, you have it with orange, and the other ones are with the new Crystal16. As you can see, the biggest difference is that actually the improvement not only in temperature but also what we can detect with transmissivity allows us actually to see much more than what we used to see here. The old Crystal16. You were not able to detect that much previously. Another big improvement of this new system is the software. For those of you that are used with our instruments, you know that if you want to analyze your data, you would have to use a separate software, the Crystal Clear software, to be able to, or use an alternative to analyze your data and plot your solubility curves, Metastable. This instrument, V3, the new industry standard, The software is all-in-one package, so you perform experiments and you also do the analysis in the same package. It's quite easy, flexible to use, user-friendly. As you can see here, you have some icons. You just quite explicit, quite easy to understand. You just need to drag them, and you have a heat to a certain temperature. You can age that temperature, cool down. You can add a prompt, so you stop. So very easy to handle, and you do not need actually that much training to be able to use such a software of this instrument. And the beauty of it is that in the same time while I'm running experiments, I can now open other data from previous experiments or analyze while I am running the experiments, the data of what is happening at that moment in my vials. And here, maybe you are used to see the clear cloud points. These are all in this software. So now you can already assign the clear and cloud points from the software. And of course, there are different ways. You also have a very automatic way, so you do not have to look yourself for the points, and you can optimize it. So that's also the beauty of it, that it really makes your life much easier. And besides all the features helping to export the graph in a certain format with the colors that I want, with the thickness of the lines of the points, data points that I would like to enrich to my presentation. So quite a lot of flexibility brings. Here is just an overview a bit of and what now the Crystal16 said, but it's able to do what I have just mentioned to you. So the temperature reach of all 4 block reactors in parallel, minus 20 degrees, which before we were able to reach only minus 10 degrees. Temperature accuracy also, we were about 1-2 degrees accuracy, and at this moment is 0.5 degrees. Transmissivity, of course, it depends what the concentration that you can detect. It depends on the compound that you are using. Of course, it's compound dependent, but for example, for carbamazepine is a compound that we use quite extensively for all our, for most of our tests. We were able to detect 1-2 milligrams per milliliter. And now with this Crystal16, we went as low as 0.5 milligrams. Quite some flexibility next to the software and the data analysis. With that said, I will stop this part and I will just go into more science and applications of what you could do on the Crystal16 instrument. And with that, I want actually to start with crystallization and why crystallization, and what are the benefits, and why to look into crystallization. Of course, if you would like to bring a solid form on the market, even if you want to bring a liquid formulation on the market, you would also want to know about crystallization, because you would like to avoid it and you would like to be able to control this. So to be able to reach this, what I have here in this picture, to produce at the plant scale, we need to consider quite a lot of parameters, a lot of factors, processes. Most of you know that it is a lot of work involved before you can even think to bring a product on that level. Solid form control, solid form, that's one of the most important, let's say, topics finding that form, optimal form, either that most thermodynamically stable form or maybe not, that you need to bring to the market, that has the right particle size, shape, particle properties, the right impurity. Control crystallization is crucial in manufacturing. And besides this, where do we start? If you think about it, how do we start before we reach this milestone, this planned production? We all start with solubility. Solubility is one of the most important information that one needs, and not even in crystallization development, whatever you start to do in the lab as a scientist. I do remember many years back, I didn't know anything about my compound. The very first thing that you do is try to find out a melting point and solubility of the compound in different solvents, to be able to understand on how to design your future experiments. Your future experiments, depending on what will be those. It will be a crystallization screen, process, you would like to make a salt, you would like to go towards a co-crystallization, or you have a chiral compound and you need to look into chiral separation, impurity. Crystallization also is a purification method at the end of the day. So it's quite important why we should look into crystallization and into solubility, and actually it's the way that we start. And we look into solubility and the importance of the solid form. Why do we look into the solid form, and what should we look for? Of course, when you bring a solid form, you look into solubility, dissolution, hygroscopicity, safety, of course, as well, but also morphology and other particle properties. And how do we start actually in the lab? We do start with, we might start with a molecule. Could be that we have already a neutral molecule that can have different forms, polymorphic forms or solvated forms, hydrate, anhydrate. But it still doesn't reach the physical-chemical properties or those that we are looking for to be able to bring it at a larger scale, that specific API. So a normal way of developing the molecule that you have, you would look into how to improve those properties. So by the first one to look into is to make a salt. If you can make a salt with your molecule, then it is one of the first ways to improve the physical chemical properties of your molecule. You can make different salts, and of course, again, the salts, they can have different polymorphic forms, so they can have different solvated forms, the same as a neutral molecule. If you cannot make salts, or salts still didn't bring the right solid form with the right properties that you are looking for, so next step in the development would be to look for co-crystals. The same co-crystals could be many different co-crystals made with different co-formers, but also the same co-crystal can have different polymorphic forms or pseudo-polymorphic forms. And last but not least, the last result in the development of a molecule, you would look into, if none of these options are working, then you would look into amorphous solid dispersion and try to as we all know, amorphous is in high energy state, high solubility and increased dissolution rate, but very unstable. So you need to find a way on how to stabilize this amorphous state. Of course, you can make different different type of amorphous solid dispersions, and I will shortly also give you a few ideas on how to do this. Need to speed up a bit. Going back to solubility, there are different methods out there on the market. Just briefly looking at one of the most common one, let's say the equilibrium, the solubility determination by equilibrium, or the HPLC method, which is quite accurate. But if any of you have done, and I'm pretty sure many of you have determined solubility by HPLC, you know that it takes quite some time, and the determination is of a concentration at a certain temperature. You do not have that much flexibility there. You need to prepare your samples. You need to leave them to equilibrate for at least 24 hours, or even worse, 48 hours, depending. In each company is also different procedures. After that, separate liquids from other liquids, from solids, dilutions, and then start to measure. Takes quite some time, a few days, until you finally have some data. Another method is the solvent addition method at one temperature for multi-component systems. I will not get into that now, but the one that I would like to say a bit more about it is the polythermal method, which was actually developed on the Crystal16 quite some years back. This method is actually quite fast. In a few hours, you can get not only one point, solubility point on your solubility curve, but you can actually have multiple points, temperature-dependent solubility curve, and implicitly you also have information about the metastable zone width and the supersaturation curve of your compound, only in a few hours. Think about it. If you would take one block reactor for one solvent, and you have in the Crystal16 4 block reactors, you can already have 4 solubility curves in 4 different solvents. Quite in a very short time, in a few hours. How it works, for those of you that do not know, so here on the left, you start with a slurry, and you have a LED light, passing through the vial and detected the light on the other side. If you have solids, the light is blocked. When you start to heat your sample, and then solids go into solution, when you have a clear solution, then the light passes through completely. You have 100% transmissivity. That's your clear point. That's your first point on your solubility curve. If you follow by cooling, then the moment that you have detect the very first particles into solution, so when your transmissivity drops from 100% to 99% and lower, those are your first points on the supersaturation curve, nucleation curve. So actually, if I want to if I want to look concentration, the graph like this one, where you have concentration versus temperature, actually your clear points, or the first points that you detect when all your solids go into solution, are the points on the solubility curve. So the points on the blue curve, these are your clear points here. And in you can imagine from the same measurement while you are, after you heat your sample and then you got your clear solution, you start to cool and then you get your points on the supersaturate, on the nucleation curve. And implicitly what you have between, you have the metastable zone. Quite important to know this if you would like to, for example, define your crystallization process afterwards. This is an example about a solubility landscape in different solvents. I will go further. This is what I wanted actually to share with you related to the metastable zone with the that I have just showed to you a bit earlier. Why is so important? And actually with the Crystal16 you can get this type of data very early in the development of an API. So depending on how your process will look like, you have different type of strategies on, for example, this is an example of sealing crystallization on how to do it, and how important it is, how it reflects in your maximizing your yield, on getting rid of impurities, on looking more into the particle size distribution. This metastable zone width is quite important. I think you all agree with me. Going even further and faster through this slide. So, well, now we have done our solubility, let's say the solubility screen. I gave you a bit of an idea actually in one run, one full 16 reactors, 4 block reactors, you can already have 4 solubility curves at once determined. So I have now the solubility and a bit of information about my compound. What do I do? What is next? Could be that is a crystallization or a polymorph type of screening. Things that I would look normally into is degree of saturation, so I would play with different concentrations, temperature, holding or aging time, cooling rate, fast, slow, will have an influence. Final temperature. There are different crystallization methods that you can take into account, like cooling, evaporation, or evaporation, crystallization from gels, layering technique, thermocycling, slurry. There are quite a few. There are others as well, like anti-solvent. I have here, do not forget about anti-solvent that not necessarily to perform it on the Crystal16, but can be done quite easily on the crystalline, for example, and vapor diffusion. That's a method really developed, a gadget specifically developed on the crystal breeder. Those two you would not do it on the Crystal16, but all the others are quite easy to perform. Controlled crystallization on the Crystal16, and the next day, if another scientist comes in the lab and wants to repeat your experiment, then you will be sure that you will get the same results, and you will not have surprises. These are a few case studies. Examples from the literature. This is a group from Hungary. They published quite some years back on from a drug of Sanofi. I think at that time the drug was known to have only 2 polymorphic forms or so, and what they tried to show is that actually if you add a bit of diversity in your crystallization screening, you can actually find much more. So just, and what they looked here, they looked a bit at chemical diversity in the solvents that they used. Like you have here acetylnitrile, alcohols, ketones, and so on, and a few crystallization methods. Even if you see here, it's not that much. It's fast and slow cooling, crystallization by evaporation, and thermocycling performed on our Crystal16. And as you can see, they found actually in total 8 forms, 2 pseudo-polymorphic forms, and the other ones are real polymorphic forms. So the more you think about your screening, you put more thoughts into it, and you choose for a bit more diversity, you will definitely find much more. And I do always remember the quote of Macron that said quite many years back, that I tend to refer every time I have a presentation related to polymorphism and crystallization. So the more time and money you spend on a compound, the more polymorphs, in other words, actually not his exact words, you will find. Another idea on how to define your crystallization or polymorph screening, again, a few parameters that you can vary here, but this is related to a study, well, multiple studies from quite a few years back, where we were looking on how to crystallize, get different polymorphic forms of different APIs. What you see here, the different colors are the different polymorphic forms. So if you would focus only on 1 or 2 crystallization methods, most probably you would not find all the polymorphic forms. I hope with this quite simple example, I can give you bit of an idea that the more we do, of course, in a smart way, smart design of your experiments, the more you can get out of this. Now another study, another case study from a different group back in 2014, where they were looking on drawing some guidelines for those poorly soluble compounds. We know nowadays since quite some time back, one of the biggest issues in also in pharma industry, but not only in pharma, is are the low, poor soluble compounds. And as you can see here, what the authors of this article from Crystal Growth managed to do, they, by using different cooling rates and playing a bit with the conditions of the different parameters of the crystallization, of influencing crystallization, they came up with actually quite common sense, with common parameters that you should look into when you deal with poorly soluble compounds. And I'm pretty sure you would agree with me that when you have that case, you need to look into high crystallization temperature. Of course, you will increase your temperature, lower degree of saturation, and slowing cooling rate. Another case study on this is another group that was looking into how to influence actually the shape of a polymorphic form by use of additives. And what they did here, actually, they used quite some different set of additives, where they were looking on how to inhibit the growth of a crystal in one direction and to promote it in a different direction. And for a specific drug they were looking into, for fluniximmeglumine, as it is here, they actually managed to change the needle shape into prismatic and plate. So depending on what is your objective, actually quite a lot can be achieved by using the Crystal16 instrument. Another one in terms of changing crystal habit, this was a part of a study where we were looking at actually solvents, different solvents with different polarity, and how they would influence the shape and size of the crystals that you can make. I think here the images are quite self-explaining for this. I'll go even faster now into this. For those of you that you have a Crystal16 already in your lab, or you will have in the future, the transmissivity data, and what you see here in green in this graph, it is quite important. It tells you much more than you think. It doesn't only tell you about the clear and cloud point, it can tell you about the size of your particles. Even if you see it a bit more noisy, it means that you are dealing with quite bigger crystals. But in this case scenario, it was part of a study where we were looking at different colored compounds, and actually for this potassium dichromate in water, which only one form is known, we actually identified that it may form a hydrate or a solvate, a hydrate actually. And this we have understood it from actually this profile, how it gets into, tries to get into solution, gets out of the solution here by seeing this peak, and then goes again into solution and crystallizes again. So once again, the transmissivity, that data from your experiments, it can tell you much more than just a simple clear and cloud point. Just to give you an idea. If you have more questions, you can send us an email, and I can share more with you related to this. Very fast going to nucleation rate and induction time measurements. There were several groups busy in the last years on defining a method for induction time measurement. A group of Dr. Horst, then the one of Marco Mazzotti, and Thomas Vetter. I remember he also had quite a few publications where actually on the Crystal16 it was a method defined on how to perform this induction time measurements in an optimal way. Again, if you would like to find more about it, I can share more in an email afterwards. And related to these, actually, and related to a webinar that I think last year was presented by René Steindam for us. He did quite some work on, of course, induction time measurement by using the feedback control feature of the software of the Crystal16, and where actually this feedback control feature helps a lot on optimizing your experiment. Here you have simple examples on how you do them. You can do solubility with and without the feedback control. So actually you can shorten a lot of the time. And of course, for induction time measurements, the added value is invaluable actually. Yeah, in this case scenario, I think this is data from René Steindam. What he used to do in about 70 hours, he actually reduced it about 25-hour time, experimental time, and how usually the transmissivity, so the temperature profile that you said it go from I don't know, 20 degrees to 60 degrees, then you go to 5 degrees, and again and again. So it's triggered by temperature. By having the feedback control, actually your trigger is on transmissivity. So what you say to the software is, when you see 100% transmissivity, you can go to the next step and you can cool. So it doesn't need to go to the maximum temperature that you have set. Sometimes you reach a clear solution before reaching that maximum temperature. So then actually you optimize, you perform much faster and smarter your experiment. So going from one step to another one. Another example from the group of Professor Marco Mazzotti a few years back in 2018, where they used the Crystal16 and the temperature cycling for deracemization. This was on NMPA, a combination of Widmer ripening and temperature cycling to enrich, actually in one of your experiment in one of the enantiomers. For those that they want to know more about it, I have here also the reference, so you can find more. A few more things just before I really need to stop. Other things that you could do with the Crystal16 in terms of solid state screening. As I mentioned in the beginning when I started this presentation, when the free molecule is not an option, we would look into salts, on how to make salts that would have a higher or better physicochemical properties than the initial molecule. I do not get into details. We also have an application note, and I always refer to a paper from 2015 where some of my ex-colleagues at Avantium Crystallics, they have done quite some work on optimal salt screening. They use different methods, in situ salt screening, where you use solid counter ion, and you add, you slurry them for some time at a certain temperature. Saturated solutions method. There are different methods out there. These are the ones stated in also in their paper and performed also with the Crystal16. So they give you quite of an idea, different ways on how to make salts in a very flexible, reliable way. As you can see here, if you use, you can either use one counter ion and 16 solvents if you want, or you use one solvent or just a few solvents and 16 counter ions. If you are working in pharma, if you want to make salts, yeah, I don't think you would need to go into 16 counter ions. I think the pharmaceutically acceptable counter ions are less than that, depending on the drug you are working on. So this is just to give you a bit of an idea what you can do with the Crystal16 from salt screening point of view. Of course, if salt was not an option, and then you need to look into co-crystallization, and not only because the salts were not an option, but you maybe would like to, even from a different point of view, to improve, I don't know, melting point, even taste masking. Co-crystallization is used for that. There are different methods on how to make your co-crystals, and here are some solution-based method: evaporation, cooling, also with anti-solvent slurring, but we also know the dry and wet kneading that can be also used. this is part. Oh, I see. I do not have the reference here. I would add it before I will share all the slides with you in an email in the coming days. This is actually a part of an article of Professor Jopter Horst many years back. We also have a webinar on this, on what actually he was doing. Was looking for an optimal, successful way to make co-crystal. So what actually you would do, you would look to the solubility of your compound. This is the ideal case scenario where the solubility, you determine the solubility of your compound, the solubility of your conformer, and ideally in a stoichiometric ratio 1:1, you will form the co-crystal. But in real life, we know that those cases are quite rare, and in a lot of cases, the solubility of the API or your compound and the conformer are quite different. Like when you look here. And then most of the cases, if we look into a 1:1 stoichiometric ratio in our experiment, you will end up most probably with a mixture of one of the components, either more of your API or more of the conformer and the co-crystal, or just a physical mixture, depending on what you have there. And actually the method, going back a bit to the basics, is that from the solubility curves of the API and the conformer, you may generate a T-clear, how you see it here. In this figure, for a sample consisting of the saturation concentration of the individual components. And if the solubility temperature of this mixture is greater than the individual components, then it indicates the formation of a more stable, soluble form, which could be a co-crystal. I go further. Here is an example from the same paper, and we also have it on one of our application notes of co-crystal formation with I think carbamazepine with isonicotinamide, 2-ethoxybenzamide, and 3-nitrobenzamide. So as you could see, you would be able to make a co-crystal, as you see here, for the isonicotinamide. It highly depends actually on the solubility of the components, and for the 3-nitrobenzamide. Go fast. Went a bit longer than I expected. As a last case scenario, let's say, to improve the physical chemical properties of your drug, you would look into an amorphous state. As I mentioned earlier, high energy state as an amorphous, that means high solubility, increased dissolution rate. Nevertheless, it's really unstable, so it can crystallize any moment. You cannot bring to the market such a form unless you stabilize it. So there are many ways on how to disperse or stabilize these amorphous formulations. And here are just, it is an example on how can you design your amorphous solid dispersion screening on the Crystal16. Here you have only the compound with additive 1, 2, and 3. I have done many other screens where you actually have more than just 1, 2, 3 additives, or in the same dispersion you use a multiple of additives to be able to stabilize your amorphous in a dispersion. Usually they are temperature cycles. You heat and cool, or you fast cool and evaporate afterwards to be able to make this amorphous solid dispersion. And here is also some data on where you see the solubility curve, and then actually the of a compound, and actually the different metastable zone. So what you see in the different colors here are actually the nucleation curves, the sperm saturation curves of the different API with the different additives. So as you can see, and related to one of my previous slide, additives, excipients, at the end of the day, can have an influence on the metastable zone with the size of your the metastable zone of your compound. I will stop here. Here is just an overview of the many applications of the Crystal16. And I'm pretty sure much more out there. We have also a booklet that my team has made it last year when we were celebrating the 16 years of Crystal16, where a lot of applications performed on the Crystal16 are stated there on the different industries. On our website, under the publication database, again, you have a lot of application notes, presentations, webinars, through the years, posters that we have produced for our customers. And with this, I would like to thank you for joining this webinar. I would like to thank my team for their support and bringing this webinar to you today. To Thomas Kendall, thank you for supporting me on the last moment to bring this through. Dan Dumitrescu, for his support on this, and Geraldine on the back, and that was always there to help me with this. And now I will try to take some of your questions. Allow me to find my mouse back, and bear with me a few seconds. Questions. Okay, so we have a few questions related to, I see that you would like to have the presentation, the slides, and I will do that. You will receive them in the coming days, if not tomorrow, the day after tomorrow. The same as the recording will be placed on our YouTube channel and also on our website. A question related to, I see here, related to crystallization screening. There are a few methods that I have mentioned there that you can do with the Crystal16, quite a lot of versatility, quite a lot of methods that you can easily use, like thermocycling slurry. You can do a shorter term, a few hours, a few days, even a week or 2 weeks. If you would like to, for example, get the most thermodynamically stable form, of course you would slurry, or competitive slurries, for example. I didn't mention this during my presentation. If you'd like to, if you have two different forms and you are not very sure about the stability, their stability at a certain temperature in certain conditions, competitive slurry is a good way to go further with that. Cooling crystallization, also the same, can be done in different fast, slow, with faster, slow cooling rates can give you quite different results, different polymorphic forms, and even size of your particles, of course. I do see another one. What is crystallization procedure for removing impurity in the ppm level? Yeah, this is at ppm level is it depends on what type of impurity you are talking about. If it's a chemical impurity, I would definitely play with the different solvents. Try to map the solubility of the compound and the impurities if it's possible, and even in mixtures, solvent mixtures, to see how you can better excludes those chemical impurities. If the impurity is another polymorphic form, yes, as I mentioned, competitive slurries could be, depending what is that impurity. You could choose quite a different, let's say, strategies. I think this is it. If you have any other questions, please do send them to us at info@crystallizationsystems.com, and we will answer your questions in the coming days. Thank you very much all for your time today, for being present at this webinar. Stay tuned. At the end of June, we come back with another webinar still related to crystallization, and hope you have enjoyed the topic today. If you'd like to know more, our website crystallizationsystems.com has quite a lot of information, or just directly contact us at info@crystallizationsystems.com. Have a good day, afternoon or evening, wherever you are. Thank you.